In this video, let's take a look at how to find the inverse Laplace transform of 2s over s squared plus 4s minus 5. To do this, 2s over s squared plus 4s minus 5, we start by using the technique of partial fractions. So 2s over the bottom factors as s plus 5, s minus 1. So I have distinct linear factors. Also, the degree of the numerator is less than the degree of the denominator. And so I can write this as a over s plus 5 plus b over s minus 1, where the a and the b are unknown constants that we have to figure out. So now I use the partial fractions very much like we did in Cal 2. And get a times s minus 1 plus b times s plus 5. Okay, from this point forward, there are two techniques that work. I'm going to show both techniques, not because I want you to do both techniques, but just so that you're aware of them. So first method number one. Method number one, let's just multiply out the right-hand side. We get 2 times s is equal to a times s minus a plus b times s plus 5 times b. Then matching the coefficients, we see that 2 is equal to a plus b, because here I have 2s, and then I've got an a here and a b here, so these have to match. Also, there is a plus 0 on the left-hand side, and so that means 0 must be equal to negative a plus 5b. And so I get a system of two equations and two unknowns, and I have to solve for a and b. This system is probably easiest by just directly adding them up. So 2 is equal to 6 times b. So b is equal to 1/3. And then if I plug 1/3 back into the top equation, that gives me that a is equal to 5/3. So that's the first technique, matching the coefficients and then solving a system of equations. This technique always works. The catch with this technique is sometimes you might have a very long system of equations. Now, method number two works as well, as long as I have linear terms over here. The method number two is, let's let s equal 1. Take this equation again, and this time let's just plug in s equals 1. If s equals 1, the left-hand side becomes 2. If s equals 1, that's a 0. And if s equals 1, I get 6 times b. And therefore b is equal to 1/3. Another very convenient number that I could plug in is negative 5. And I choose negative 5 because that would make this one go away. So if s equals negative 5, here I get negative 10 on the left-hand side. And then I would have a times negative 6 on the right-hand side. And so dividing, I would get a is equal to 5/3. So either way, I get the same answers. The second method tends to be a lot faster if I have distinct linear terms. Okay, so the practical upshot is that we get this is equal to 5/3 over s plus 5 plus 1/3 over s minus 1. Okay, so now let's figure out the inverse Laplace transform of 2s over s squared plus 4s minus 5. To do this, we consult our table of Laplace transforms and see if we can find anything that looks like this. Well, looking here at the table, I see that if I have something of the form 1 over s minus a, the Laplace transform is e to the at. And I'm not going to worry too much about the values for which it converges. So for this part, I would have 5/3. Instead of a, I've got a plus 5 here, so my a is negative 5, so e to the minus 5t. And then this part would be plus 1/3, and then here I have s minus 1, so I'll have e to the 1t. And so that would be the inverse Laplace transform of this rational function.